Hello, I am Joe van de Vijver and I will present you our work towards robust cardiac segmentation using graph convolutional networks. Starting from the basics, for cardiac segmentation we start with an ultrasound image of a heart and we want to segment the regions of interest, like so. Now, several methods have been proposed over the years to solve this problem, but the most common way of doing this nowadays is to use the deep learning architecture UNet, as most of you probably know. Several studies have shown impressive results using UNet, with average accuracies comparable to inter-observer variability. Now, while the average accuracy of this approach is comparable to human annotators, its worst-case performance is a lot worse. And this lack of robustness remains a fundamental problem for cardiac segmentation. With this problem in mind, a recent MICAI publication showed the feasibility of using graph convolutional networks for cardiac segmentation. Graph-based networks for segmentation approach the problem in a fundamentally different way. Instead of predicting a label for each pixel, these methods will predict the coordinates of the contour points of the structures of interest. This means the model is solving the same problem, but in a fundamentally different way. The architecture of the graph convolutional network starts by applying a CNN encoder to the ultrasound image. In this case, we use a pre-trained MobileNet v2 architecture, and the output of the encoder are features embedded in a latent space. The second part of the network is the decoder. It starts by transforming the single-dimensional embeddings into an abstract keypoint embedding space. In our case, we use 107 keypoints with a starting embedding size of 32. We then apply the actual graph convolutional layers, which are in fact normal convolutions but over the key points. We do this for several layers until we arrive at the output, which is the coordinates of the key points we are predicting. In this work, we will build further on this architecture and provide three main contributions. For our first contribution, we expand the model to multi-structure segmentation. The original work proposing the method did only do left ventricle, so single structure segmentation. Now, the straightforward approach would be to just predict more key points. But when we tried this, we saw that the model often fails in a way where it confuses the points of the inner and outer ring of the myocardium. It would often flip these two concentric rings or produce overlapping predictions. Our proposed solution is to, instead of predicting the coordinates of the outer ring, we predict the distance of the myocardium at each point. This clinically motivated constraint results in a model that always produces clinically valid shapes. For our second contribution, we did an ablation study of the decoder part, the actual graph convolutional part, on the public CAMUS dataset. We did several experiments, but our most important one varies the size of the graph decoder. Surprisingly, we found that we can shrink the decoder as far as removing it completely without affecting the average die score significantly. This shows that it is in fact the encoder that is doing most of the work. We also compared to NNUNet, and there is still a statistically significant gap in average die score between the graph model and UNet. When we look at the worst case behavior of the two models, we see something interesting. While the UNet produces weird shapes and disconnected parts, the graph-based networks always produces anatomically correct shapes, although they can be wrongly placed. So both methods fail in a very different way because they tackle the problem fundamentally differently. This was a motivation for our third and final results, where we compare the outputs of both models. The idea is that we run both architectures in parallel and look at how well they agree. For this experiment, we used the Hunt4 dataset. It is a large in-house clinical dataset where the images were actually used in practice to do clinical measurements. To quantify the agreement between the models, we calculate the die score between the segmentation outputs of both networks. We see that for most cases, the agreement of both networks is high, but we also have a long tail of cases with low intermodal agreements. So for our experiment, we defined a lower and higher threshold of 0.8 and 0.9 dice, and we then took 100 cases above the high agreement threshold and 100 cases below the low agreement threshold. We then asked the clinician to annotate the images on image quality, view correctness, etc. When only looking at image quality, we can already see a significantly lower number of high quality cases for the samples with low agreement. We also see a lot more unsuitable cases when the agreement is low. Unsuitable means the image should not be used for any clinical measurement, and in fact is it a garbage input. Remember that we are dealing with a raw clinical dataset. When we add the information about the view correctness, we see that the majority of the low agreement cases were actually the wrong view. The model is trained only on apical 2 and 4 chamber views, and we expect these to also be in the validation set, but this is not always the case in practice for various reasons that I will not go into now. We have a similar situation when we look if the image is left ventricle focused or not. Finally, out of the 100 cases with low intermodal agreement, only 7 cases remain without some sort of problem, and all of them are low quality. So this tells us that the intermodal agreement can be used to catch bad inputs. One use case can be to filter bad quality data in data mining applications. Another application can be to give real-time feedback to the user of the automatic segmentation tool to warn for faulty segmentations in real time. I will finish this presentation with a real-time demo that shows exactly this. Finally, I would like to thank my co-authors. It is truly a privilege to work together with these brilliant researchers. Thank you for your attention.